Howdy, this is Browdy. So this is discussion 7.2. This is the first of the second semester discussions, and I've explained this in class, but discussion 7.2 comes right after 6.1. So because that weird semester division, we have 6.1 right into 7.2, so they're really all one big unit. So if you're wondering where 7.1 was, that's what's up. Let's jump right in. So if unit 6 or 6.1, naming and formulas, if that's just about being able to get a formula from a name or a name from a formula, that's great. But it's not an insanely useful thing on its own, right? It's kind of like an empty party trick. It's like, hey, you see that formula right there? I can name it. Okay, well, that's cool, but that doesn't really do you much good, right? So unit 7 is really where we start to apply those main concepts. And so the very first top part of this here is actually kind of the main things we need to understand about chemical equations and chemical reactions before we jump into like the main part of unit 7. And so 7.2 is all about different types of chemical reactions. And if you're like, well, when did we learn about chemical reactions? Actually, way back in unit 2, we learned about physical and chemical changes and properties. Well, a chemical reaction is just a chemical change, but we represent it very specifically. And so I'm going to kind of go out of order here and you'll see why. So first and foremost, a chemical reaction itself is just a chemical change, and it's some sort of change or some sort of phenomenon that happens to matter where the chemical composition of some type of matter becomes something else. So the chemical composition of something changes. Now, we talk about the different parts of that very specifically. So we can say that's a chemical reaction. And we can say that there's reactants, which are the things that react. There are the products, which are the things that are produced. And then for a chemical equation, we represent that with an arrow. And so a chemical equation is just a representation of a chemical reaction with the reactants on the left side of a yields arrow, which I'll talk about in a second, and the products on the right. So the way we could see that is here, the reactants yield the products. And so you could say yield or give or produce or make or whatever. This is kind of like the equal sign in an equation in math, except it's not equals because it's directional, right? So these react to produce this. The reactants react to yield or to make or to produce the products, right? And so there are a few things that we use to describe these. So state symbols describe the physical state of the substances involved in a reaction. So S refers to solid, L, which will often be cursive, if I handwrite it, is liquid, G is gas, and AQ is aqueous, which refers to being dissolved in water. So you'll typically see this with like a metal compound or a salt compound that's dissolved in water. And so that will describe the states of the reactants or the products. Excuse me, but we have a few other things to talk about. So first and foremost, there's evidence that chemical reactions have taken place, and we've actually learned all of these before. Formation of a gas or fizzing or bubbling, right? Formation of a precipitate, which is when a solid comes out of the solution. Release or absorption of heat or light, so just energy. And then unexpected color change. All of those could be indicators that a chemical reaction has taken place. Beyond that, you can actually consider odor change to be one as well, but because we don't really want to encourage you to smell things in the lab, that one's not really included. Now, the last thing before we move on to the types of chemical reactions are the diatomics. These are 7 elements that don't exist as single atoms in nature. So they exist in pairs. So they're still pure elements. So H2, for example, refers to hydrogen. When hydrogen exists in nature, you're never going to find just an H, just a single H atom, and say, oh, that's hydrogen. Hydrogen will exist as H2, and that's because it has one valence electron, and that wouldn't be stable. So it's easier for hydrogen to pair with another hydrogen. And when one valence electron and one valence electron pair covalently, they each have satisfied their valence shells, or they've completed their outermost energy levels, and so they're satisfied now. The same thing applies to nitrogen. 2 nitrogens would form a triple bond. Fluorines would form a single bond, and oxygen, and iodine, and chlorine, and bromine. Each of those would be unstable if it existed by itself. But when they pair up, they can be stable. And so we have hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. Now you can remember these with the mnemonic, have no fear of ice cold browdy. I like that to be school appropriate. It doesn't rhyme as well. There's your normal mnemonic, but I like to put browdy at the end. So have no fear of ice cold browdy. Remember that how you'd like, but for me, that works. And so again, these are just things that you will never see as just one of them in a reaction. So if I were to say, for example, hydrogen and oxygen interact to produce water, it would be H2 plus O2 yield H2O. And so when I describe them, if I say pure hydrogen or oxygen, I'm referring to H2 and O2. So the oxygen gas that we breathe is O2. And that's that. Now we can move on to the different types of reactions. So the first is a combination reaction. So as the name implies, it's when 2 or more substances combine to form a single substance. These can also be called synthesis reactions, and you can call them either one. I'll accept both. Now, as annoying as it might be, when we look at chemical equations for now, I want you to ignore the 2's here, or the coefficients. So the numbers in front of the elements or compounds, for now, just ignore them. In 7.3, we're going to talk about balancing equations, and so those will be relevant, but for now, as annoying as it might be for you, it is for me, just ignore those. We'll talk about them later. So here what we're saying is that magnesium solid and oxygen, remember O2 is oxygen gas, combine to produce or to yield magnesium oxide solid. Now some people tend to get hung up about how O2 and Mg can combine to MgO. Well, where's the 2? And that's because magnesium and oxygen, if you say this out loud, right, magnesium plus oxygen gives you think in your head, magnesium oxide. And you're right, it gives you magnesium oxide. But because Mg is plus 2 and oxygen is minus 2, they combine in a 1-to-1 ratio. So this is where the Unit 6 stuff starts to come in. If you say magnesium oxide, I'm going to expect that you know how to write that out. And that's going to happen all the time for Unit 7. So let's show a few more examples of this. Here we have nickel, 3 specifically, so nickel with a charge of plus 3, and iodine, that's just pure normal iodine, but it's I2, right, because it's diatomic. Nickel and iodine combine to produce nickel iodide, which makes sense, right? Because nickel plus iodine gives you nickel 3 iodide, because it's nickel 3. But how do you write the formula for nickel 3 iodide? Well, nickel is plus 3, and iodine is minus 1, so NiI3 is nickel 3 iodide. Here, aluminum and oxygen combine to form aluminum oxide, right? When you say it as a sentence, it just makes sense. Aluminum and oxygen, so O2, combine to form aluminum oxide. But aluminum is plus 3, oxygen is minus 2. We crisscross, and aluminum oxide is Al2O3. So you have to write the correct formula for aluminum oxide. Potassium and nitrogen, right? Potassium and nitrogen react or combine to produce potassium nitride. When you say it as a sentence, it just sounds right. And it is. Potassium nitride is the answer. But how do you write potassium nitride? So you have to use your Unit 6 knowledge. Potassium is plus 1, nitrogen is minus 3, so K3N. And that's combination reactions. That's all it is. It's 2 substances combine to form 1. Now the opposite of that is a decomposition reaction. So if something decomposes, it breaks down into its parts, and that's what's happening here. It's when a single compound breaks down into two or more products. Okay? And so here we see solid calcium carbonate breaking down into calcium oxide solid and carbon dioxide gas. Okay? So one thing breaks down into two or more. Here, if we start with calcium oxide, CaO is calcium oxide, think about the name and think about what that would break up into. Calcium oxide would break up into calcium and oxygen, right? So calcium is Ca, but oxygen is O2 because it's a diatomic, because that's what oxygen is O2. So calcium oxide breaks up into calcium and oxygen. CaO yields Ca and O2. Another one is aluminum bromide. Just think about the name, aluminum bromide. Oh, well, that probably breaks up into aluminum and bromine. And it does. But aluminum bromide is AlBr3. Aluminum is just Al, and bromine is Br2. So don't let the different numbers confuse you. We'll deal with balancing that next unit or next subunit. But for now, I just want you to write the correct amount of atoms, or the correct formulas for each. Here we have silver chloride, right? Just AgCl. And that breaks up, as you would expect, into silver and chlorine. Silver is Ag, chlorine is Cl2, because it's a diatomic. Okay, so these are combination and decomposition reactions, and admittedly, they're pretty straightforward. Now, single replacement reactions are a little more involved. So this is where atoms of one element replace the atoms of a second element within a compound. And so if we look here, excuse me, talking in this mic always makes my throat a little dry. So we have magnesium solid and aqueous silver nitrate. So this is a solution in water of silver nitrate. Now, if you look at the products, you have magnesium nitrate and silver by itself. Specifically silver solid and aqueous magnesium nitrate. So what that means is that the magnesium solid replaced silver in silver nitrate to give you magnesium nitrate, right? You switched the metals here. So these just went, whoop, they switched. Magnesium was by itself and silver was with nitrate. Now magnesium is with nitrate and silver is by itself. So it's a single replacement. But you have to look at the formulas. Here we had AgNO3 because silver is +1 and nitrate is -1. When you switch those out, you have to write the correct formula. So what I encourage you to do is read the sentence or read these equations as a sentence. Say the products, predict the products as a sentence, and then write them down from the correct names to the formulas. So magnesium magnesium reacts with silver nitrate to produce magnesium nitrate and silver. Magnesium nitrate has Mg, which is +2, nitrate, which is -1, so it's MgNO3 2 in silver. Now there's one more step to these. I'm going to scroll down to the next page. Here we had magnesium replacing silver. And for single replacement reactions, you want to look at the back of this page, or the second page of the PDF. And we see the metal activity series. Single replacement reactions only work if the metal that's doing the replacing is more reactive than the metal being replaced. And so here, magnesium was replacing silver. And in this case, magnesium is more reactive than silver. The most reactive metals are at the top, the least reactive metals are at the bottom. So a single replacement reaction will only happen if the metal that is doing the replacing is higher on this than the metal being replaced. And since magnesium is higher than silver, it works. So now let's do a few more. Here we have silver nitrate and copper. Copper 2 specifically. So we have to see, can copper 2 replace silver nitrate? So we look. Where's copper? And here's silver. So copper is more reactive than silver, and so the reaction will work. Copper 2 can replace silver. So we'll end up with copper 2 nitrate, which is CuNO3 2, right? Because plus 2 minus 1, and then silver by itself. So the cheesy example I like to use of this is it's kind of like nitrate is the hot date, right? And silver is going out with nitrate, right? But silver's kind of batting out of its league. They run into copper 2. And copper says, hey, nitrate, I see that you're with silver. I'm better. I'm more reactive. You should leave silver and come with me. Nitrate is just listening to the reactivity, the activity series, and it says, silver, I'm sorry. Copper is more reactive. You got to go. And so copper replaces silver, and you end up with copper nitrate, and silver is now by itself. It's a cheesy example, but that's kind of how it works. It's going to go with the more reactive metal. Here we have magnesium and zinc phosphate. Is magnesium more reactive than zinc? We look. Here's magnesium, here's zinc. It is, so the reaction proceeds. So you end up with magnesium phosphate, so Mg3PO4 because magnesium is plus 2, phosphate is minus 3. Okay? And then zinc by itself. So again, I encourage you to say the sentence out loud. Magnesium reacts with zinc phosphate to give you magnesium phosphate and zinc. So then you can write magnesium phosphate as you know it should be, and zinc is by itself. Now this one is a little different. You have copper trying to replace zinc in zinc chloride. But does that work? Is copper more reactive than zinc? It's not. So to go back to my initial example, the kind of corny date example, if chloride is the hot date and it's out with zinc and they run into copper 2 is like, chloride, I see you're with zinc. I'm better. You just got to trust me. And chloride, is just going off the facts. And it looks at zinc, it looks at copper, it says, I'm sorry, copper, but zinc is just more reactive. You're bluffing. And so in this case, no reaction occurs. You can just write NR for that. Because copper is less reactive than zinc, the reaction will not proceed. Because copper just can't replace zinc. Zinc is more reactive. And so the anion, the negative portion, will favor the more reactive one. Lastly, we have sodium and iron 2 carbonate. Because this is minus 2, there's only one of these, so it's iron 2 carbonate. Can sodium replace iron? And sodium can replace iron. And so sodium will replace iron to give you sodium carbonate, Na2CO3, and then iron by itself. Iron plus 2 to be specific. And those are single replacement reactions. Okay, and that's all it is. We have 2 more kinds. We've got double replacement reactions. And so single replacement was straightforward in the name, and double replacement is that exact same thing, but doubled. So it's the exchange of positive ions or cations between 2 reacting compounds. So here we have iron 2 sulfide and hydrogen chloride. Sorry, I want to call it hydrochloric acid. Iron 2 sulfide and hydrogen chloride, and the positive portion switches to give you hydrogen sulfide and iron 2 chloride. Okay, so the hydrogen and the iron literally just switch. And so, again, these just switched. So H went with S, Fe went with Cl. And now you can notice the state symbols here. And we're not going to worry about this too much, but in the first example, I'm going to discuss this a little more. So here you have solid iron sulfide and iron 2 sulfide and aqueous hydrogen chloride. And those are giving you hydrogen sulfide gas and iron 2 chloride aqueous. So the state symbols will become important, and I'll talk about why here shortly. In this first example, we've got sodium chloride and lead 2 nitrate. We know it's lead 2 nitrate because nitrogen is -1. If there's 2 of them, there's a -2 charge and 1 lead, so lead 2 nitrate. So sodium and lead are going to switch. So you'll end up with sodium nitrate, which is just NaNO3 because +1 -1, and lead 2 chloride, so PbCl2. And that's it. You just switch the positive portion, the cation. Now, I said I'd talk about the state symbols a little bit more. We're not going to deal with this just yet, but in double replacement reactions, we will often look for a precipitate, because remember, a precipitate is a sign of a chemical reaction. And so the way we do that is we look at these two compounds that we end up with as the products. One of them will typically be aqueous, meaning it's dissolved in water, and often one of them will precipitate. It will form a solid. And so the way we figure that out is by looking at the bottom here at the solubility rules table. So the first compound we're looking at is sodium nitrate. And so we look here and we find sodium on the positive portion. So there we see sodium. And now we have to find nitrate. So we go over until it lines up with nitrate. So we have sodium nitrate. And here there's an S. S means that sodium nitrate is soluble in water, meaning that it will be aqueous. So sodium nitrate will stay aqueous in a solution. What about lead chloride? So here we find lead 2, and we go over to chlorine. So lead chloride is I, insoluble in water, and that means it does not dissolve in water. So if lead chloride is formed in a solution, it will actually precipitate out and form lead chloride solid. And so we use this chart to figure out which product in a double replacement reaction will precipitate out of the solution. Now, I'm not going to ask you to do that a lot in 7.2, but I want you to be familiar with how to do that as we go forward. So here, this would stay aqueous, and this would precipitate out of the solution and form a solid. But we're not going to do that with the rest. Now here, just like I've been recommending, we're using the words, the sentences. And so it's saying iron 3 chloride reacts with sodium hydroxide. If it's a double replacement reaction, what do? We replace the cations. So you'll have iron 3 hydroxide and sodium chloride. And that's what you have. Now, if we were to write these out, iron 3 chloride would be FeCl3 plus NaOH, because 3 minus 1 plus 1 minus 1 would give you iron 3 hydroxide, so Fe parentheses OH3 plus NaCl. And that would be your equation. Lastly, you have copper sulfate and lithium hydroxide. You switch lithium and copper to get lithium sulfate, Li2SO4, and copper 2 sulfate, but copper 2 hydroxide, so copper OH2. And that's it. Those are double replacement reactions. The last kind that we have are combustion reactions. Combusting is what it sounds like. It's burning something. And so a combustion reaction is when a carbon compound, so here we have carbon, is burned in oxygen, so O2, to form carbon dioxide and water, CO2 and H2O. Now this is actually most of the cellular respiration equation. What it's saying is glucose here, solid sugar, is burned in the presence of oxygen gas to produce carbon dioxide gas in liquid water. Here we have methane, CH4. This is actually what was in your hands when I lit them on fire on Halloween. Halloween, whatever. And this is a carbon compound. It's got carbon in it. And so methane reacts with oxygen gas to produce carbon dioxide and water. Now, don't worry about, sorry, I'm ignoring a call here, but don't worry about the coefficients yet. So for now, just know there's a carbon compound and oxygen giving you CO2 and H2O, and we'll worry about those coefficients in 7.3. And that's it. Those are your 5 types: combination, decomposition, single replacement, double replacement, and combustion. That's it for 7.2. I will see you all in 7.3, and I hope this is helpful. Take care.